So I'm here to record the lecture 2 again because I just gave a really bad lecture, so I just decided to record it again by myself. So because there is no audience, I may just be very brief. And the first part is the high school math we may use. We may use like this and this and this today. And for other part, they are really easy, so I just skip it. So first we begin with some history stuff. There was a guy called Gutenberg. He invented the movable type printing, and so the knowledge can spread in textbooks. So you can use the movable type printing to create textbook, and they can spread knowledge. And in the very beginning, the digit is like expressed in Roman numerals, so they are very difficult to carry out some arithmetic. So that's a bad way. And at this time, the Indian invented the decimal system that we use today, and it's very clear and neat. So all the mathematics and all the technology just developed based on the decimal system. And there's a guy called this, and he record all the basic methods like arithmetic methods such as adding, multiplying, dividing, and other stuff in a textbook. And the textbook was spread to Europe. There was a guy called Fibonacci. He found that the textbook is very promising, and he just introduced it to Europe. And after a lot of time, the Europes finally just accept the decimal system, and they call all the basic methods such as the adding, multiplying, these stuff, they call them algorithms. So that's the word algorithm comes from. So I need to keep two words in mind or notion. The first one is data structure. It means how to store data, and the other is the algorithm. It's about operations on data. And the next, I gonna introduce the Fibonacci sequence. So Fibonacci is nowadays most famous for the Fibonacci sequence. It's just the number is the sum of the last one and the one before the last one, right? And to write it in mathematics, it's something like this. And when n comes to infinity, the next element divided by the past element is the golden ratio, right? And the Fibonacci sequence magically appears in a lot of fields such as biology, demography, architecture, and music. And so a lot of biology patterns appears to be like the numbers of the dark blue ones is, I don't know, maybe 21, and the light blue one is 13, right? And these are elements in Fibonacci sequence. I don't know why. And in this picture, a small rabbit becomes a big rabbit in the second month, and she gives children every month after that. 1 children per month after the second month, and small children becomes big rabbit and gives 1 children every month. The total numbers of the rabbit is Fibonacci sequence, and this is the most famous visualization of Fibonacci sequence. Like here's 1, 1, 2, 3, 5, it's this is 5, this is 8, something like that. And for this rectangle, you just take a square out, and the next rectangle is in similar shape of the original one. Okay, so the Fibonacci sequence grows at exponential speed, so I give a proof. It's really easy, I think. Maybe you can read it here by yourself. And so after that, I'm gonna introduce a very important notion called recursion. It's a function calls itself. Like here is the definition of the function, and it calls itself in the function, right? So this is recursion. A function calls itself. And so it's like the n is the input, and there are two if and else. We return the sum of the last element and the one before the last element. This is really easy. And so how should we measure this is an algorithm, right? So how should we measure the speed of these algorithms? So a naive idea, maybe we use a timer, but it does not work because different computers just have different speed, and if you use a timer, the fast computer certainly take less time. And so at last we use the number of computer steps because it can just do not take the hardware or the computer itself in consideration, and we can make analysis in theory. So what is the basic computer steps? It includes arithmetic, integer arithmetic, right? And comparison is just if else, and assignment like write or read data. We may not use this today. We're gonna use arithmetic and comparison. So there are basic computer steps, and like 2 plus 3, this is one computer steps, right? And if elif else, this is 3 computer steps. Okay, so we should so the input of an algorithm, like for this, for example, in Fibonacci 3 and Fibonacci 9999, they must take different time, right? So we should use a function to take the input size into consideration. So we actually use a function with respect to input size to measure the speed in total, right? And next I'm gonna tell about this algorithm in detail, and I draw a recursion picture. It's a tree. So I'm calculating Fibonacci 5, and because I first encountered 2 if, right, it doesn't satisfy, so I go to else, and I return Fibonacci 4 and Fibonacci 3, and the Fibonacci 4 goes here again, and it returns 3 and 2, and this guy returns 2 and Fib 1, right? And Fib 1 is 1 because I go into this if, right? And they are similar, right? So how to measure the runtime of this Fibonacci recursion algorithm? So you can see that the process that you carry out this algorithm is basically a recursion tree, and actually the Fibonacci 5 equals the the time of carrying out Fibonacci 5 is actually equal to the Fibonacci 4 plus Fibonacci 3 plus 3. What is the 3? It's the 3 if comparison here, right? And Fibonacci 4 is equal to Fibonacci 3 and plus Fibonacci 2 plus 3 comparison. And so we can say that the runtime of Fibonacci n is equal to n minus 1 plus n minus 2 plus 3. And you can see that the expression here is basically the Fibonacci sequence itself, right? So actually the runtime of calculating Fibonacci sequence using a recursion algorithm is actually almost the same runtime as Fibonacci sequence, almost the same like growth as Fibonacci sequence, right? And here is plus 3, so we know that Fibonacci sequence grows at exponential time, like here, and it's really obvious that 3 is a little number compared to exponential growth. So the Fibonacci sequence recursion algorithm actually grows at exponential time. So this is called a runtime analysis, or we measure the speed of an algorithm, right? So it grow at exponential time, so we express at O2n. I'm gonna tell you what is the big O notation in the following part. And for this algorithm, the Fibonacci 200 will take almost forever to calculate. So the computer cannot even give the answer of Fibonacci 200. This is ridiculous, right? So we're gonna introduce another algorithm called dynamic programming. So what is dynamic programming? It's basically we store the result of subproblem, then we use the result of subproblem to calculate the big problem, right? And for example, the subproblem is fib2 and fib3. We store the result of fib2 and fib3, and we can use them to calculate fib4, right? Let's see the algorithm. So this is the fibdp, it's dynamic programming, and we start with a list. It's 0 and 1, and we write a for loop, and the list append the sum of the last two element in the list, right? And we return, so we have a long list, and we finally return the last element, which is fib list n, right? And this is dynamic programming, so we store all the result of subproblems in this list, and we use the result to calculate the bigger ones, right? So this actually, let's do some runtime analysis. So here is one computer step, right? So we first we assume that all the elements in the list are integers, okay? And there is one computer steps because it's an addition of two integers, and there's a for loop. We run it for a lot of times, like n times, right? And for n times there's one computer step, so it seems like there are totally n computer steps. But this is not accurate, right? Because we know that Fibonacci sequence grows exponentially, and it will become very, very large numbers very soon, right? And so it's very obvious that like 2 plus 3 equals 5, and a large number, I don't know, maybe a very large number in Fibonacci. These are two large numbers in Fibonacci sequence, and their addition is certainly going to take longer time than this one, right? Because it's a very large number, maybe more, I don't know. And so we should measure the addition more accurately. So basically there are like two n-bit number doing addition, right? So this is actually so in computer the numbers are binary. Maybe I'm gonna tell you why the numbers are binary in some computer architecture lecture in the future, but in computer it's not decimal, it's the numbers are binary, and for example 53 in decimal system is something like this. And actually 1 bit, so this is 1 bit, 2 bit, right? And 1 bit addition is taking 1 computer steps. So this is 1, and n bit is n computer steps in total. So this addition is not 1 computer steps, it's actually n computer steps. And the for loop runs this addition for n times, so in total it's n squared computer steps in total. And this is a polynomial, and we call it linear time. Okay, so the runtime is linear. Oh, maybe not linear, it should be square or polynomial. It must be a typo. Okay, so we should keep in mind that the integer addition takes 1, it means 1 computer steps, and n-bit addition takes like n computer steps, right? So we move on to the asymptotics finally, and we already seen that we maybe let me show you some code first. Where's my mouse? Oh, why it's so slow? Okay, so let me show you something. What is this? So this is the like 1 divided by the golden ratio. I don't know. And so we calculate log 2 and 0.618 in this way in Python, right? Because the math.log is the base is e, maybe, I think, and we use the formula like this to calculate the log base 2 and 0.618, and I'm showing you the element in Fibonacci sequence divided by the next one is equal to 0.618, and maybe it's 1 divided by the golden ratio, and I'm showing you something like the limit, right? And it's becoming like more and more close to 0.618. So this is something called limit in calculus. Okay, so here is the fib recursion algorithm, and we're calculating FIB 40, right? And it's a very large number already. It takes about 56 seconds. This is crazy, a long time. And the Fibonacci dynamic programming algorithm calculating the 40 element is only about, it's connecting, right? And it's very fast. Okay. So they are calculated the same thing, right? And the speed is, this one is exponential time and this one is polynomial time. That's the difference, okay? And that's the power of algorithm. So good algorithm really saves a lot of time and even turns some problems into computable, right? This is almost incomputable, not computable, right? And okay, fine, I'm going to tell you this part next, and I'll show you the exponential time and polynomial time. And actually there are a lot of other stuff. This is like more neat one, so we start by this, and the exponential time, the polynomial time. These are some like concrete examples, and there's something called log linear. It's log n, right? And linear is n, or this stuff is equal to n, and the log n and the const. So I've shown you that the exponential and the polynomials, they have a very large difference or gap in the runtime. I just show you the code, right? And similarly, when n goes to infinity, each of them has very large gap in the runtime. So if you can turn an algorithm from this to this, you make a very big progress, okay? So here I just make the formula more detailed, and you may use them in the material, okay? And I'm giving you an example to show you what's the big O notation. So the big O notation, like f is 3, g is log n, h is 4. There are 3 functions, okay? And these two are constant time. G is log n time, right? And f equal to OG. These are 2 functions, and the big O notation is basically saying that f is less or equal than g, the runtime, when n goes to infinity, okay? So like f is like this, and g may be smaller in the first place, but when n goes to infinity, it's a very large gap that f can almost be omitted, okay? Like here I achieve 999, you only achieve like 100, so you can almost omit it, right? And this is the big O notation. This is similar to the limit stuff, and similarly this is almost the same, except that it means that g or f bigger or equal than g when n goes to infinity, right? And f and h here, they are both constant time, and we use this notation to show that they are in they are in the same category. Okay. So the main idea is that we only focus on the big picture and we do not care about some very trivial stuff. And the first one is the above rules here. And the second one is we omit the multiplicative constants, like if I got an algorithm, its runtime is 14n squared, and we say that they are O(n) squared, right? We just omit the multiplicative constants here. And so for polynomials here, and we only take the dominant part. So in polynomials, the n to the 4 is bigger than n to the 3, bigger than n to the 2. So in the limit formula, we say that if b is less than a, then when n goes to infinity, the n to the b divided by n to the a is almost 0. This means that n to the b can be omitted. Okay. So n to the a is dominate n to the b, right? And if I got an algorithm whose runtime is like n8 plus n7 plus 3, and we know that n to the 8 is dominate the other part, so we see that this is O(n)8, right? And for log, it's different, okay? Because log, no matter what your base is, they are almost the same runtime. So I'm showing you the formula here, and so we just omit the base. Okay, if you see an algorithm whose runtime is like log 100, and we just say that it's log n. Okay, and log n, the base is equal to 2 for default. Okay, and they're the same, so the base equal 100 is the same as base equal 2, right? And for exponential, it's again the same as polynomials. So really the 4 to the n is bigger than 3 to the n, bigger than 2 to the n, right? We write it in the limit stuff. It's limit n goes to infinity, like if b is less than a and b to the n, a to the n is equal to 0. Okay, so we say that if we meet some formula like 5 to the n plus 3 to the n plus n squared, and we know that polynomials is dominated by exponential, and this is the big one in exponential, so it's basically 5 to the n, right? And I'm gonna show you some code too. So here I show you 5 functions. The blue one is log n, the orange is n, this is n log n, this is n to the n squared, this is 2 to the n, right? And you can see that in the long run, so maybe in the beginning they are almost the same, but in the long run they will have very different large gap in the runtime. So I'm showing you that when the x-axis, which is the n, when it comes to 1000, so this code means that I go from 1000 to 1005, and I pick 100 points to connect the dots to get the function line. And here the x-axis, which is n, is 1000 to 1005, and the n and log n, they already have very large gap, right? So this one can almost be omitted. Similarly, the n log n is far bigger than n, and n squared is far bigger than n log n. And by the way, 1e6 means 10 to the 6 here. So the y-axis is actually, this is 1 multiply 10 to the 6. Okay, this is 0.2 multiply 10 to the 6. And similarly, here is the exponential and the polynomial. They have very large gap because the y-axis is multiplied by 10 to the 32. So here is a large gap, right? Here is far larger gap. Yeah, it may look like they are very near, but remember that we are multiplying by 10 to the 302 here. And I'm showing you some limit stuff, like the limit is equal to 0. 10 to the minus 20 is almost 0, right? And lastly, I'm showing you that why no matter what is the base for the log, they are almost the same, because I'm showing you 4 log lines here, and you see they are almost the same, but the n is far larger than all of them, and they seem just really near to each other in the long run. Okay, so that's why no matter what is the base, we always say that it's log n, which has 2 for the base for default. And these are all the code, and I'm giving you a last example here, and we're doing some exercise. So basically this stuff, the n to the 4 dominates this thing, and we delete the multiplicative constant. We got O n to the 4, right? Similar for this is very small compared to the polynomials, and here this is really smaller than the constant, and here the exponential dominate the linear, right? And sine is something like this, so it's actually almost the same as constant, right? So the n squared dominate all the stuff. We got n squared here. Okay, so that's the lecture.